All right, let's keep rolling. Week 2, number 10, maximum depth of a binary tree. 104, given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. Okay, so we just did a binary tree problem recently, and we followed the template. So let's see if this problem can also do our template. So there's a 9 here, there's a 10 here, oh, it's a 20. Actually, these don't matter, so these might as well be letters. Okay, so what is a leaf node? Well, I'm going to make these green. These are leaf nodes. And why are they leaf nodes? They're leaf nodes because there's nothing to the left, there's nothing to the right. So you can imagine if they wanted to take any information from the left or the right. So if you took the function and you call it with a node, and the node is none, you can imagine this returns 0, right? What's being returned to these is 0. What about here? So this is the interesting piece, right? This has a node on the left and a node on the right. So what values does it want to receive from the left node and the right node? Well, let's think about our template. I'm going to go ahead and write the template down. And let's say we have a solution function. We have some results variable. It could be a list, it could be a number, it could be something. I'm just going to put a squiggly line there. We're going to define some type of go function. The go function is going to take a node. The solution is going to take the root. We're going to call the go function with the root. In the end, we probably eventually return something in the results, right? Probably. We're gonna make sure we do a base case, right? The first thing that we're going to handle in this go function. We're going to call left, and then we're going to call right, and then we're going to do some logic, right? This is our template. We bring this up every time. It's very useful. The solution function gets a root. We have some results variable. We may or may not need it, but just to say that we have something available to us. We're defining a function. So what's our base case? If we look at a tree, and we think about this in the recursive setting, and we're calling the recursive function on this B and this C, what do we want returned out of here? Well, we want any logic that it has with its own children, right? Propagated upwards. So if nones are returning 0, presumably this would return 1. This would return 1 to the root node, and then this root node could decide whether there's a maximum depth that is coming from the other direction, right? For the sake of argument, let's just say this B here, it returns a 6, right? This C here, let's say it's a leaf, has nothing, so these return 0 to it. This returns a 1. So this 10 can decide whether the 6 or the 1 is larger. It could choose one of them. And what this 10 is probably going to do is want to return a 7 up to this 3. So we already have a sense of what's being returned, right? It's whatever is the larger of the left or the right. So this one's left, this one's right. I guess green's already taken. Go ahead and make this blue. The larger of the left or the right, then that's what plus 1 is going to be returned to the parent. So yeah, that's the crux of this problem. I mean, I actually don't think there's any more. We've already written the code. Let's just write it into here, right? So results, I'm actually not sure what it is yet. Could be nothing. Go ahead and make this larger so you can see it. Go ahead and move this to the side. So we're going to define go. Inside of go, we're going to do, it's going to take a node. There's going to be some base, and the base we're going to call left, right? So call left. We're going to call right, and then we're going to do some logic using that left and right, and then we're going to go ahead and call go with the root and return results. Now, this template is something we bring up for binary trees. It's not always what we need, right? So this template works really well if what we're trying to do is accumulate some type of max, accumulate some type of aggregate, and change results, mutate that variable results. If you think about this one, I'll go ahead and fill out the base. It's possible the results are not needed at all. So what's the base case here? If node is null, if node is none, let's return 0, right? And what's the call to the left? Node.left. Node.right. And what's the logic? Well, we want the maximum, right? So the max from children, let's call it, is the maximum of from left and from right. And this is what we want to propagate, right? We want to return 1 plus this max from children. So actually, let's walk through this. This B here. Let's do the real example. So this B is going to return 1 upwards, right? That's the from left. If you're calling it from the 10, the C, this is the from right. It's going to return upwards. Now, what's the max from both? It actually doesn't matter because they're the same. This 10 is going to return 1 plus those, right? What's 1 plus those? 1 plus 1 is 2. It's going to return 2, right? Same thing on the left side. Like, what does this 9 return? This 9 returns the max of, 0 and 0, 0 plus 1. It returns a 1 upwards. What is this 3 going to return? This 3 is going to return, it's going to look left and right. 2 is the larger of it. And then it's going to return 1 plus this 2, right? So it's 3. So the maximum here would be 3. Now, let's think about this. Should the root return 3? Let's look at this. Let's look at the example. Example 1 is so the root does return 3 because the root has its own representation. Now, look at line 24. We're not actually using the result of this. So what we could actually do, because we're not in any of this code mutating results, we can delete results. If we delete results, we can't return results. But we can return go. We can return the invocation of go on root. And what we're going to get returned to the function, right, return to the solution, is a function called on the root. So let's see this, and let's try this and see if there's anything we're missing here. Okay, these are accepted. And it's not super illuminating looking at the passing test cases. It's actually sometimes better to look at the failing ones if you want to fix something. All right, so it's accepted. And importantly, we have a good baseline of how to think about some binary tree problems using this template. It's not always the same. We don't always need results. Sometimes, right, we delete results, don't return results, we're returning the recursive call on the root. Thanks so much, everybody. This has been a pretty good problem to do back to back with the other problem that we did. If you want to look at the other one, go to week 2. And we did this one earlier today. We did diameter of a binary tree. That's a really good one. I'm going to go ahead and check this off and sign off. Please leave a comment for any problem you'd like to see that's not on this list in order, and I'll go ahead and pick it up. It's a long 8 weeks. Well, looking forward to it, and I'll see you guys next time.